There's two things here, the main topic and the meta topic. The main topic is a neat algorithm for solving many different two-dimensional equations. That is, things that have two unknown real numbers, or perhaps those involving a single unknown, which is a complex number. So for example, if you want to find the complex roots of a polynomial, or some of those million-dollar zeros of the Riemann zeta function, this algorithm would do it for you. This method can be super pretty, since there's a lot of color involved, and more importantly, the core underlying idea applies to all kinds of math, well beyond the algorithm that we're talking about, including a little bit of topology, which I'll talk about afterwards. But what really makes this worth 20 minutes or so of your time is that it illustrates a lesson much more generally useful throughout math, which is to try to define constructs which compose nicely with each other. You'll see what I mean by that as the story progresses. To motivate the case with functions that have 2D inputs and 2D outputs, let's start off simpler, with functions that just take in a real number and spit out a real number. If you want to know when one function, f of x, is equal to another function, g of x, you might think of this as searching for when the graphs of those functions intersect, right? That would give you an input where both functions have the same output. To take a very simple example, imagine f of x is x squared, and g of x is the constant function, 2. In other words, you want to find the square root of 2. Even if you know almost nothing about finding square roots, you can probably quickly see that 1 squared is less than 2, and 2 squared is bigger than 2, so you realize, there's going to be some solution in between those two values. If you wanted to narrow it further, maybe you try squaring the halfway point, 1.5, and this comes out at 2.25, a little bit too high, so you focus on the region between 1 and 1.5. And I'm sure you can see how you'd continue this, you just keep computing the midpoint and chopping your search space in half. Another way to think about the same process, which is going to make it easier once we get up to higher dimensions, is to instead focus on the equivalent question of when the difference between the two functions is 0. In those terms, we found a region of inputs where this was negative at one end and positive at the other end. And then you split that into two, narrowing our attention to a half whose outermost points, again, produced varying signs. And you can keep going on like this forever, taking each region with varying signs on its borders, finding a smaller such region among its halves, knowing that ultimately, you have to be narrowing in on a point where it would hit exactly 0. So in short, solving equations can always be framed as finding when a certain function is equal to 0, and to do that, you use the heuristic if f is positive at one point and negative at another point, you'll find a solution somewhere in between, at least if everything changes smoothly with no sudden jumps. Now, the amazing thing that I want to show you is that you can extend this kind of thinking into two-dimensional equations. Equations between functions whose inputs and outputs are both two-dimensional. One example that comes up all the time is complex numbers, which are two-dimensional, and the tool we're developing here is perfect for finding solutions to complex equations. And since we're going to be talking about these 2D functions so much, let's take a brief sidestep to consider how we illustrate them. Graphing functions with 2D inputs and 2D outputs would require 4 dimensions, which isn't going to work so well in our 3D world on our 2D screens. But we still have multiple good options. One is to just look at both the input space and the output space side by side. Each point in that input space is moving to a particular point of that output space. And maybe I could show how moving around an input point corresponds to certain movements in that output space. And by the way, all the functions we're going to consider today will be continuous, in the sense that small little wiggles in the input only cause small little wiggles in the output, no sudden jumps. Another option would be to imagine the arrow from the origin of the output space to the output point, and then attach a miniature version of that arrow to the input point. What this can do is give us a sense at a glance for where a given input point goes, or where many different input points in the whole plane go, by drawing the full vector field. And of course, if I'm doing this very literally, you can see it gets a bit cluttered. So one common thing to do is to shrink all of the arrows to be smaller and the same size. And looking at this, you can get a sense just of the directions of all of the output points. But perhaps the prettiest way to illustrate 2D functions, and the one that we'll be using most this video, is to associate each point of the output space with a particular color. Here we've used hues, that is where the color falls along a rainbow or a color wheel, to correspond to the direction away from the origin, while we've used darkness and brightness to correspond to the distance from the origin. For example, focusing just on this ray of outputs, all of those points are red, and the ones closer to the origin are a little darker, the ones farther away are a little lighter. And focusing just on this ray of outputs, all of the points are green. And again, closer to the origin is darker, farther away is lighter. And so on. All we've done here is assigned a color to each direction, changing continuously. And you might notice the darkness differences here are pretty subtle, but for this video, all we're going to care about is the directions of the output, not the magnitudes. The hues, not the brightness. The only important thing for you to remember about the brightness is that near the origin, which has no particular direction, all of our colors fade to black. Okay, so once you've decided on the colors for each output point, you can do something pretty cool. Color all of the input points based on where the function takes them into that output space. Personally, I like to imagine a whole bunch of points from that input space hopping over to their corresponding outputs, and then getting painted based on the color of the spot where they land, and then hopping back to where they came from. Doing this for every point of the plane, it gives us a way, just by looking at the input space, to understand roughly where the function takes each point. For example, we see some pink points in the upper left here, and what that tells us is that all of those points are going to get mapped in the pink direction, the lower left of the output space. And those 3 points you see in the input space, which are black with a lot of colors around them, those are the ones that go to 0. Alright, so solving equations here. Just like the 1D case, solving any kind of two-dimensional equation can always be reframed as asking when a certain function is equal to 0, or in this case the 0 vector. So that's our challenge. Create an algorithm which finds the input points that a given 2D function takes to 0. And you might point out that if you're looking at a color map like this, just by seeing the black dots, we already know where the zeros of the function are. So does that count? Well, keep in mind that to create a diagram like this, we've had the computer compute the function at every single pixel on the plane. But our goal is to find a more efficient algorithm that only requires computing the function on as few points as possible, only having a limited view of the colors of the plane, so to speak. And also, from a more theoretical standpoint, it'd be nice to have a general construct that gives us the conditions for whether or not a 0 even exists inside a given region. Now, remember that in one dimension, the main insight was that if a continuous function is positive at one point and negative at another point, then somewhere in between it has to cross over 0. And this begs the question, how do you extend that into 2 dimensions? You would need some sort of analog of talking about signs. Well, one way to think about what signs are is directions. Positive means pointing to the right along the number line, and negative means pointing to the left along that number line. And two-dimensional quantities also have directions, but for them, the options are much wider. They can point anywhere along a whole circle of possibilities. So in the same way that for one-dimensional functions, where we're asking, is it positive or negative on the boundary of a range, where the boundary is just 2 points, in 2 dimensions, we're going to want to look at the boundary of a region, which is now a loop, and ask about the direction of the function's output along that boundary. For example, take a look at this loop around this 0. The output goes through every possible direction, all of the colors of the rainbow. Red, yellow, green, blue, and back to red, and every color in between along the way. But on this loop over here, with no zeros inside of it, the output doesn't go through every color. It goes through some of the orangish ones, but never, say, blue or green. And that insight is promising. It looks a lot like how things worked in one dimension. Maybe, in the same way that if a 1D function takes both possible signs on the boundary of a 1D region, there was a 0 somewhere in the middle, we might hypothesize that if a 2D function hits outputs of all possible directions, all possible colors, along the boundary of a 2D region, somewhere inside that region, it must go to 0. So that's the guess, and take a moment to think about if this should be true. Then, if so, why? Well, if we start thinking about a tiny loop around some input point, we know that because everything is continuous, our function takes it to some tiny loop, near whatever the corresponding output point is. But look, most tiny loops in the outputs barely change in color. If you pick any output other than 0 and draw a sufficiently tight loop near it, the loop's colors are about the same as the color of that point. A tight loop here is all bluish, a tight loop over here is all yellowish. You certainly aren't going to get every color of the rainbow. The only point where you can tighten loops around it while still getting all of the colors of the rainbow is the colorless origin, 0 itself. So it is indeed the case that if you have loops going through every color of the rainbow, tightening and narrowing in on one point, then that point must be a 0. And so, let's try setting up a 2D equation solver analogous to the one-dimensional equation solver we had before. When we find a large region whose border goes through every possible color, split it into 2. And then, well, look at the colors on the boundary of each half. In the example shown here, the border of the left half doesn't actually go through all colors. There are no points that map to the orangish-yellowish directions, for example. So we'll gray out that area as a way of saying we don't want to search it any further. Now the right half does go through all colors, spending a lot of time in that green direction and then quickly passing yellow, orange, red, as well as the blue, violet ones. Remember, what those colors mean is that points of the boundary get mapped to outputs of all possible directions. So we want to explore this region further, subdividing again and checking the boundary colors of each subregion. The boundary of that top right one is all green, so we'll stop the search there, but the bottom one is colorful enough to deserve another subdivision. And just like the 1D case, we should be able to continue on indefinitely, getting arbitrarily close to some 0. Each iteration, you check if a subregion has a boundary covering all colors, meaning points of the boundary get mapped to all possible directions, and you just keep chopping those subregions in half. And so there you go. Hang on a second actually, what happened here? In that last iteration, neither of the subdivisions on the bottom right actually went through all colors. So our algorithm stopped because it didn't find anything with all colors around the boundary, but we didn't narrow in on a 0. Clearly, something is wrong here. And being wrong is a regular part of doing math. We had this hypothesis that led us to a proposed algorithm, so somewhere along the line we were obviously mistaken. Being good at math is not about being right the first time, it's about having the resilience to carefully look back and understand our mistakes and how to fix them. Now in this case, the problem is that we had this region where the border went through every possible color, but when we split it down the middle, neither of the subregion's borders went through every color. We had no options for where to keep searching next, which broke the 0 finder. Now in one dimension, this sort of thing never happened. Anytime you had an interval whose endpoints had different signs, when you split it up, you knew that you were guaranteed to get some subinterval whose endpoints had different signs. Put another way, anytime you have two intervals whose endpoints don't change signs, when you combine them, you get a bigger interval whose endpoints don't change signs. But in 2 dimensions, you can take 2 regions whose borders don't contain every color, and then combine them to get a region whose border does contain every color. And this is the way that our 0 finder broke. And in fact, if you think about it more, you can get a big loop whose border goes through every possible color without there being any zeros inside of it. Now that's not to say that we were wrong in our claims about tiny loops, when we said that a forever narrowing loop that continues going through every color had to be narrowing in on a 0. But what made a mess of things for us is that this "does my border go through every color or not" property doesn't seem to combine in a nice predictable way as you put regions together. But don't worry, it turns out we can modify this slightly to a more sophisticated property that does combine nicely, which will give us what we want.